Hello and welcome to our lesson on right triangles. Specifically, what we're going to be doing today is looking at ways to find missing sides and then a little bit of finding missing angles when we have a right triangle. So for starters, what does it mean to have a right triangle? Well, if we have a right triangle, that means we have a triangle that has a right angle in it, and that right angle is signified by that little box in the corner of our triangle. So the triangle I have here is an example of a right triangle. And in the right triangle, the two sides that make the right angle. So this side here and this side here, these two sides are creating that 90-degree angle. Those are called the legs of the right triangle. So the legs, which we'll identify as A and B, so we'll call this side A, we'll call this side B, and really those could be interchanged. Those are what we call the legs. Okay, they make the 90-degree angle in the right triangle, and again, they are interchangeable. So I wrote A as the vertical leg and B as the horizontal, but I could have flip-flopped those. So they are interchangeable. Okay, and then the third side of our right triangle, let's this one here. The third side is the longest side of the right triangle, and it's the longest because it corresponds with or is across from the largest angle, the 90-degree angle. So across from that biggest angle is our longest side. We're going to call that one C, and it is known as the hypotenuse of our right triangle. So C is the hypotenuse, and it is the longest side because it is opposite of the biggest angle. And again, this is across from or opposite of the 90-degree angle. Okay, so those are the parts of the right triangle. You're probably familiar with that. You've seen this before. So what we're going to look at is hopefully review, but it could be a long time since you've seen some of this stuff. The ways in which we can find missing sides, not all the ways, but some of the ways in which we can find missing sides and ultimately missing angles in a right triangle. So one of the easiest ways to find missing sides is using the Pythagorean theorem, and this can be used when two sides of the right triangle are known. So the Pythagorean theorem says that a squared plus b squared has to equal c squared. That is, the sum of the squares of the legs of the right triangle will equal the square of the hypotenuse. And again, this can only be used if we know two sides, and then we solve for the third side. Okay, so for example, in triangle 1 here, we have the legs of our right triangle, so we could call this side A and we could call this side B, or vice versa, but the unknown side is our hypotenuse, so C. So if we were to plug into our formula, we would say that a squared plus b squared equals c squared. So in this case, 5 squared plus 12 squared has to equal c is still a variable, still unknown, so that stays in there as c squared. Now 5 squared is 25, 12 squared is 144, and if we add that together we get 169, and so c has to be what number squared makes 169, or if we want to continue to solve here, we take the square root to get rid of that square, and we see that c is going to be 13. Now, it's technically when we solve a quadratic like that, taking the square root, we put in a plus or minus, but the negative option wouldn't really apply here as we're looking for the length of a side of a right triangle. So c is going to be 13. That's a pretty common one, the 5, 12, 13. It's what we call a Pythagorean triple, one that occurs often. If you wanted to commit 5, 12, 13 to memory, that would save you a bit of time here and there. Okay, let's try another. So in this next one, we have one of our legs. I'm going to call it A. We also have the hypotenuse here, but we're missing another leg. I'm just going to say that it's B. And again, if you had switched A and B, not a big deal. So in this case, we have 8 squared plus some other leg squared equal to 12 squared. So 8 squared is going to be 64. B, we don't know. 12 squared is going to be 144. And now if we want to solve this one, we're going to have to move the 64 over. And so b squared is going to be equal to 144 minus 64 is going to leave us with 80. And then not as clear as the last one where we knew the square root of 169 was going to give us 13. We don't know the square root of 80 exactly, so we're going to go ahead and square root both sides. So we're going to say b is going to be equal to, again, we don't need the plus or minus, but in this case we're going to break down that radical 80. So it's not exact, but it can be simplified. Let's see, that's 2 and 40, 2 and 20, 2 and 10, and then 2 and 5. So we're going to be able to take out, let's see, we got some 2's there and some 2's there, so 4 out of the radical, and then a 5 is going to stay in. So we're going to say b is equal to exactly 4 radical 5, or approximately the square root of 80 is going to be not quite 9. We can approximate, though, with a calculator if we want, so it's about 8.9. Okay, so 8.9. If you want to make sure that you broke down the radical correctly, which I guess I should do here, I can also type in my simplified form and make sure it gives me the same decimal amount. So the exact answer is going to be preferred when we have no context, as we do here. If we were looking at some contextual situation, then we would probably want to use the approximate answer. Okay. All right, we got one more here. If you want to try it out, this might be a good place for you to pause the video and do that. So we are given C. And we're given, again, one of our legs. I'm going to call it B this time. And we're missing another leg, which A or B doesn't matter, but let's live one and one the other. So in this case, we're going to say that sum A squared plus B, which is 4 squared, has to equal C, which is 10 squared. So we have A squared and 16 equal to 100. If we subtract 16 from both sides, then we're looking at a squared equal to 84. And again, we're going to square root both sides to solve for a. We cannot square root 84, but we can try to simplify that. So if we were to break down, 84, 84 is 2 times 42. That's going to be 2 times 21, and that's going to be 7 times 3. So we're going to be able to take a 2 out. And then we're going to be left with 7 and 3, or 21, inside of the radical. So we're going to say a is exactly 2 radical 21, or approximately, let's see, square root of 84. It's going to be a little over 9 this time. And we end up with about 9.2. And again, out of context, the exact answer is preferred, which is why I boxed that one in. If we were to throw some context in, we would probably want to use the decimal approximation. Okay, so that's Pythagorean theorem. You've probably seen it before, but good for us to review nonetheless. Now, there are some other ways to find missing sides of right triangles that, gosh, you may not have seen since you've taken geometry in high school. So if we have what we call a special right triangle, then we can actually find the missing sides knowing just one of them. Now, we also have to know it's a special right triangle, meaning it's got special angles in it that creates patterns for us. So if only one side of our right triangle is given, then the other two missing sides might be something we can find using the patterns found in special right triangles. And the special ones are those that have 45, 45, and 90-degree angles. So it's, again, a right triangle. If the other two angles are equal, that's going to tell us something about the sides. And then 30, 60, 90 are the other ones. Again, this is a right triangle, but where the other two angles are 30 degrees and 60 degrees, there are some patterns that occur in the side lengths. Okay, so we're going to focus on the 45, 45, 90s for a second here. If we have a 45, 45, 90 triangle, and I didn't give you a good picture here, but the angle measurements and the side lengths correspond. So like in the original picture I showed you, C is the longest side because it's across from the biggest angle. So if we have an angle that's like in the middle of the other two, we would have a side length across from it that's in the middle in terms of lengths from the other two. Now in this case, if the two angles are equal, that means the two sides across from them, this side here, and let me get off my highlighter because that's terrible. the two sides that are across, so across from this 45-degree angle is this side, and across from this 45-degree angle is this side. If those two angles are equal, those two sides have to be equal. So if those two sides or angles are equal, those two sides are going to be equal. So knowing that this side has a value of 1 means this side's going to have a value of 1 as well. And now technically we could use Pythagorean theorem to find that third side, but again we're going to see some patterns occur here. So if I had 1 squared and 1 squared equal to c squared, 1 squared is 1, so 1 and 1 is going to make 2. That means that c is going to have to be the square root of 2. So we're going to have a square root of 2 here. Okay, if we go to the next one, if this side is 2, this side's going to have to be 2 because those angles are equal, those sides will be equal. And then if we use Pythagorean theorem, 2 squared and 2 squared is going to equal the hypotenuse squared. Well, that's going to be 4 and 4, which is going to make 8. And so c is going to be the square root of 8, and the square root of 8 is going to simplify. 8's 2 times 4, which means a 2 is going to come out and a 2 is going to stay in. So we're going to end up with a 2 radical 2 here. Okay, and I'm making a mess here. I apologize, but I'm trying to go kind of quickly. All right, and if we look at number 3, or this third example, if this side is 3, the side's going to have to be 3. The legs have to be equal if those two acute angles are both 45 degrees. And now if we use Pythagorean theorem, 3 squared and 3 squared has to equal c squared. So that's going to be 9 and 9, which is 18. So that means c is going to be the square root of 18, which is going to simplify. 18 is 2 times 9, which means a 3 is going to come out. So we're going to get a 3 and a radical 3 here. Okay. Now I could give you more and more examples, but the point here is to not have to use Pythagorean theorem because there are patterns occurring with these sides. Notice in the first triangle, side length of 1, side length of 1, 1 radical 2 in the hypotenuse. Side length of 2, side length of 2, 2 in front of the radical 2 for the hypotenuse. The leg is 3, the leg is 3, and then it's 3 in front of the radical 2 for our hypotenuse. And that pattern is going to occur every single time we have a 45, 45, 90 triangle. So the legs have to be congruent. Okay, whatever this leg measures, this leg is going to also measure. And the hypotenuse is just the leg length multiplied by a radical 2. So we take whatever the leg length is and we multiply it by a radical 2. Or in reverse, we could divide by a radical 2 to figure out what that leg length is going to be. So looking at these triangles here, noticing that it's a 45, 45, 90, that the one leg is 5, the other leg has to be 5, and the hypotenuse has to be 5 times the square root of 2, 5 radical 2. Or working backwards here, if I have a 45, 45, 90 that has a hypotenuse length of 8 radical 2, then the leg lengths have to be 8. And then again here, 45, 45, 90, so leg of 12, hypotenuse of 12 radical 2. Okay? So something that, I don't know if you've seen that before, but is helpful to know so that if we encounter a 45, 45, 90, we can quickly figure out the missing sides. Okay, so that's one of our special right triangles. Another one is our 30, 60, 90. Now, this pattern is not as easy, but still helpful to know. So I started out by giving you two sides here. If I used Pythagorean theorem, I could say 1 squared and 1 radical 3 squared is equal to c squared. So 1 squared is 1, radical 3 squared is going to be 3. That means that c squared is going to be 4, which means that c has to be the square root of 4, or 2. So we're going to have a 2 here. And then if we look at the next example, we've got 2 squared plus another leg squared equal to 4 squared. So that's 16, that's going to be 4. If I subtract that 4 over, a squared is going to equal 12. So a is going to be the square root of 12, which we can simplify. That's 2 times 6 and 2 times 3, so a 2 comes out and a 3 is left in. So that means this leg is going to be 2 times the square root of 3. Okay? Now again, I used Pythagorean theorem there because I knew 2 of the sides, but ultimately I should be able to find the missing sides only given you one of the sides because again, there's a pattern. So the smallest side is across from the smallest angle. Okay? If we double that side, if we double it, 2 times 2, we're going to get to 4. Again, the smallest side is across from our smallest angle. If we double it, we're going to get to our hypotenuse every single time. Okay, so if we know that smallest leg, we double it to get our hypotenuse, that pattern is going to be true every time. And again, if we know that smallest leg, to get from that smallest leg to the other leg, the middle length side there, it's 1 and then 1 radical 3, and then notice here 2 and 2 radical 3. If we take that smallest leg and just multiply by radical 3, it's going to give us the side length of that longer leg every single time. Okay, so again, maybe not as clear. Oops, this was supposed to be a 2. This is going to be a 2 radical 3. But the shortest leg, that's the one that is across from the smallest angle. Let's call that side x. Okay, the hypotenuse is always double what that length is. So if this side length was 2, this is going to be 4. If this was 3, this would be 6. If this was 8, this would be 16. So if we're going to call that x, then this side length is going to be 2x. And then if this one was a 3, this would be a 3 radical 3. If this was a 5, this would be a 5 radical 3. If this was a 7, this would be a 7 radical 3. If this was a 10, this would be a 10 radical 3. So whatever that shortest leg is, to get the longer leg, which is across from the bigger angle, we just multiply by a radical 3. Okay, again, helpful to commit to memory because if we see these, we can easily find the missing side. So again, here's our smallest side. I know it's the smallest side because it's across from the smallest angle. So if I double that, my hypotenuse has to be 6, and if I multiply it by a radical 3, my longer leg has to be 3 radical 3. Okay, this time I know my longer leg is 7 radical 3, which means the shorter leg has to be 7. So instead of multiplying by radical 3, I divide it out. And now that I have the smaller leg as 7, if I double that, my hypotenuse has to be 14. Okay, or here, if I have my hypotenuse as 10, I can cut that in half. That's my longest side. If I cut that in half, then my smallest side has to be 5. And now that I have my smallest side, multiply it by a radical 3 to get my longer side. Okay, so again, helpful patterns to know when those triangles come up. Now, if we don't want to commit those things to memory, it's totally okay. We can still find missing sides of a right triangle knowing one of the sides if we know one of the acute angles, which technically means we would know all the angles in the triangle. But if only one side is given, like in these, if I only gave you the 3 here and you didn't want to commit to memory the 30, 60, 90 pattern to know that this would be a 3 radical 3 and that this would be a 6, you don't have to commit that to memory. Another way we can find the missing sides is using sine, cosine, and tangent. So we would find these missing sides using trig ratios. That's what these are. These trig ratios called sine, cosine, and tangent. And sine is abbreviated SIN, and even though it's abbreviated SIN, we still read that as the word sine. And then cosine is abbreviated COS, but again, we're still going to read that as cosine. So we're not going to say sin here, we're not going to say cos here, we're going to say sine, we're going to say cosine. Okay, we're abbreviating for writing purposes, but we still read the full word. Okay, and then the same thing for tangent. Tangent is abbreviated as tan. And it's a little more common for you to hear that said as tan, but tangent, we technically want to read these abbreviations as the full words. So sine, cosine, and tangent, these are trig ratios that help us find missing sides and angles of right triangles. So trig ratios can be used to find missing sides. They can also be used to find missing angles. And to help us try to remember the ratios, and ratio is a fancy word for fraction, okay? There's an acronym that's been created to help us remember which ratios go with which one of these trig functions. So if you've never heard of it before, SOHCAHTOA is designed to help us remember the trig ratios that are associated with sine, cosine, and tangent. The SO part, the SOH part, that's to help us remember that the sine, and I'm going to abbreviate, my eraser is too gigantic, that the sine of an angle is going to be equal to a ratio of the opposite leg divided by or over the hypotenuse. So sine is opposite over hypotenuse, and I'm going to show you how all this works in a minute. Just kind of go with me for a bit here, okay? So helps us remember that sine is opposite over hypotenuse. And then we have the k part, SOHCAHTOA. Ca is for cosine. It helps us remember that the cosine of an angle is going to be equal to a ratio, which is a fraction, of the adjacent leg over the hypotenuse. Again, that's cosine is adjacent over hypotenuse. And then the TOA part, sounds funny to say it like that, is to help us remember that the tangent of an angle is going to be equal to a ratio of a fraction of the opposite leg over the adjacent leg. So again, tangent is opposite over adjacent. Okay, so in order to use these three trig ratios, sine, cosine, and tangent, to find missing sides or angles, you have to be able to identify the hypotenuse of the right triangle, which I think we can do because it's got to be opposite of the 90-degree angle. It's got to be the longest side. But we also have to be able to identify which leg is either adjacent or opposite to the angle that we're going to be looking at in our triangle. Okay, so opposite and adjacent are always associated with legs. There is an opposite leg to your angle, there is an adjacent leg to your angle. And the hypotenuse isn't going to move around. The hypotenuse is always the longest side of your triangle. But depending on what angle you're looking at, the opposite and adjacent legs could change. Okay, so looking at this triangle, leg A is this guy right here. We would say that it is opposite, it is across from angle Y, but it is adjacent to, it is next to angle X. So leg A is opposite of angle Y, but it is adjacent to angle X. Adjacent meaning right next to, and opposite meaning across from. Okay, so opposite is across from, and adjacent is next to. Okay, so then if we were looking at leg B is right here. Leg B is opposite of angle X. It is across from angle X, but it is adjacent to angle Y. So leg B is opposite angle X and adjacent to angle Y. And then it doesn't matter what angle we're looking at, the hypotenuse doesn't move. The hypotenuse is always across from that 90-degree angle, so side C is our hypotenuse. Okay, so adjacent is next to our angle, opposite is across from our angle. So let's try to set up some trig ratios. Again, not doing anything to solve here, just so we can get the hang of the concept. So if I wanted to write a trig ratio for the sine of angle X, so angle X is right here. SOHCAHTOA, remember the SOHCAHTOA, this acronym is supposed to help us remember what goes with what. That's the sine of our angle. Okay, that's the first part of our SOHCAHTOA, is supposed to be a ratio of the opposite leg over the hypotenuse. So sine is opposite over hypotenuse. So if we want the sine of X, we have to write a fraction of the opposite leg over the hypotenuse. So for X, the opposite leg would be 4, and the hypotenuse would be 5. So our ratio for the sine of X would be that opposite leg over that hypotenuse, which is 4/5. Okay, if I wanted the sine of angle Y, angle Y is over here, then opposite of angle Y would be 3. So now 3 is the opposite side, and then the hypotenuse is still 5. So for the sine of angle Y, the ratio of opposite and hypotenuse would be 3/5. Okay, there's the SO part. And then the cosine. When we're looking at the cosine of an angle, cosine is adjacent over hypotenuse. So let me get rid of this. Okay, if we're looking for the cosine of angle X, I need a fraction, a ratio of the adjacent side, and 3 is adjacent to angle X over the hypotenuse, which the hypotenuse is not going to move. That's going to be 5. So a ratio for the adjacent side over the hypotenuse would be 3/5. Okay, if I wanted the cosine for angle Y, angle Y is here. Well, 3 would be opposite, so I'm going to have to fix this. Okay, if I want adjacent to angle y, that would be side 4, and then the hypotenuse is still 5. So adjacent over hypotenuse for y would be 4/5. Okay, and then lastly, oops, I can leave this. The hypotenuse is not going to move. If I want to look for the tangent of my angle, tangent is our opposite leg over our adjacent leg. So tangent for x is here. I'm not going to be using the hypotenuse in this one. Tangent, I want the opposite leg over the adjacent leg. So this leg is adjacent, it is next to x. This leg is opposite, it is across from. So opposite over adjacent would be 4/3. Now if I switch that to angle y, then I have to switch these around. Okay, if I'm looking at angle y, then this side is next to it, and then this side is opposite of it. And this is your hypotenuse, which is, I know it looks like it's next to y, but that's your hypotenuse. So opposite and adjacent have to be legs. Okay, so the tangent for y would be the opposite over the adjacent side, which would be 3/4. So you can see how these things move around depending on what angle you're looking at. Okay, so you have to remember that the hypotenuse doesn't move, doesn't change. Okay, but opposite and adjacent can vary depending on the angle you're looking at, but they have to be legs. So opposite and adjacent refer to legs. Okay, so if we want to use these trig ratios to solve, which is what we're going to do in just a second here, then we are going to start by labeling only the information that's given, only the given info. What is given to us are we given, according to the angle, an opposite side and adjacent side, the hypotenuse. And then based on what we're given, we are going to write the trig ratio that corresponds. So if we're given O and H correspond with sine. If we're given A and O, okay, that's opposite and adjacent, they correspond with tangent. Or if we're given A and H correspond with cosine. So based on what we're given, we're going to write our trig ratio, and then we'll solve. And the solving part actually is the easy part. Okay, so let's look at our first example here, and I like to just have my SOHCAHTOA handy. When I'm working on these problems, I will often just write that at the top of my paper and just reference it over and over and over. So SOHCAHTOA, okay, looking at what we have here. This is the angle that we're given, this 35-degree angle, and we have the leg that is next to it, so this is the adjacent leg, and I'm going to call that A, adjacent leg, and then we have the leg that is opposite of it, and so I'm going to call that the opposite leg. Notice the hypotenuse, not labeled here, so I'm not going to label it, not going to use it. Okay, I have the 35-degree angle, I have the leg that's opposite, I have the leg that's adjacent. So because I have O and A, that tells me to use tangent. So the tangent of my angle, in this case 35 degrees, so the sine, cosine, and tangent always correspond to our angle. So the tangent of our 35-degree angle is going to be equal to a ratio of my opposite side over my adjacent side. So tangent is opposite over adjacent. In this case, it's going to be x over 24. So there's our equation. Okay, so it'll be tangent of our angle and then a fraction of our sides. Once we have it, what I like to do is make this side a fraction by putting a 1 under it, and recognize that the tangent of an angle or the sine of an angle or the cosine of an angle, it's just going to be a decimal amount that we can retrieve from a calculator. But if I want to solve this, I'm going to make the one side a fraction by putting a 1 under my trig function, sine, cosine, or tangent. That way I can cross multiply. So if I want to solve for x here, x times 1 is going to be x, and then when I cross multiply here, I'm going to have to multiply 24 by the tangent of 35. And so x is going to equal, we go to our calculator, and let me get rid of this stuff. I wonder what mode my calculator is in. 24, let's find out. There's two ways to measure angles, which is why I'm saying this. I need to go to this guy, tangent of 24 And you see how it gives me a negative? I know that negative's not going to be correct for that side length, which tells me my calculator's in the wrong mode. So where do we... Oh, there we go. Okay, so sorry, I had a moment. I forgot how to do this in Desmos. And if you're working with like a TI or a Casio graphing calculator, you're going to probably have to change the mode in your calculator too. But in Desmos, I'm going to the little wrench up in the top right-hand corner of the Desmos screen where I can access some settings. And at the bottom, there's a setting for what we call radians, and then there's another one for degrees. And we want our calculator to be in degrees because that's what our angles are measured in here. Radians is something that we'll talk about in the future, but for now we want angles in degrees. So now that we're in degrees, we should have a more reasonable answer, and about 10.7 looks good. So this is not exact. We're going to say this is approximately 10.7, and that's a reasonable amount for the leg of that triangle. So about 10.7. And I know I numbered these odd here, but I'm going to jump down to this problem. All right, so looking here, according to the angle that we're given, this leg is adjacent to that angle, and then this is my hypotenuse. So A and H, they correspond with cosine. So I'm going to use cosine here. So to set this up, I'm going to say the cosine of my 49-degree angle has to equal, remember it was cosine is adjacent over hypotenuse. So the adjacent side, which is 10, over the hypotenuse, which is x. So I'm going to make this side a fraction, and I'm going to cross multiply. So 10 times 1 is going to be 10, and then x times the cosine of 49 is just x times the cosine of 49, where again cosine of 49 is just some decimal amount. So if I want to actually solve for x here, I have to divide that cosine of 49 over. So x is going to equal 10 divided by the cosine of 49. So that's my exact answer, and that is approximately, let's find out. It's a calculator. 10 divided by, let's go into functions and put in the cosine of 49. And we get about 15.2. And I knew it was going to be longer than 10 since it was the longest side of my triangle. That seems reasonable enough. Okay? Not so bad. And let's try another one here. So in this third triangle, we have this angle, and according to the angle that we're given here, this is the opposite leg, and this is the hypotenuse. So if I have O and H, I'm going to be using sine. Sine is the one that corresponds with O and H. So the sine of our 65-degree angle is going to equal, again, sine is opposite over hypotenuse, so the opposite side, which is x, over the hypotenuse, which is 20. Make this side a fraction, and then cross multiply. So x times 1 is going to be x, and then 20 times the sine of 65 is just 20 times the sine of 65. And again, sine of 65 is just some decimal, so don't make the mistake of multiplying 20 and 65, because those are not two whole numbers that we can multiply. So we're going to be looking at approximately, it has to be a number less than 20, since 20 is the longest side of the triangle. So that was 20, and then sine of, I forgot, 65. And about 18.1, which seems reasonable enough. Alright, so there's that guy. Now, I mentioned this a bit ago, but sine, cosine, tangent can also be used to find missing angles. So let me show you how that works. Okay, looking at number 11 here, this example. Starting the same way, it's just our variable you can see is in a different spot. If I wanted to find the missing leg here, I could definitely use Pythagorean theorem because I know 2 of the 3, but I'm looking for an angle in this one. So this angle is what I'm looking for, and according to this angle, this is the adjacent side, and this is the opposite side. So I'm going to use tangent. I'm going to say that the tangent of my angle, which is x here, has to equal my opposite over my adjacent, so 15 over 12. Now in this one, the solving is going to be a little different. I know over here I end up multiplying and dividing because I'm trying to undo multiplication or division, but over here I'm trying to undo a tangent, and it's a different thing, okay? Something that we probably haven't seen in a very long time. But the opposite of tangent is just that. It's the opposite, remember, is another word for inverse. So the inverse of tangent is what we call inverse tangent. Okay, so inverse tangent, you're going to see here, if you go into functions, remember the notation for inverse is the little -1. We actually have an inverse tangent here. So inverse tangent. So in this case, we're going to say that x is going to equal the inverse tangent of our ratio. Okay, this is saying the tangent of some angle has to equal 15/12. If we put that into the calculator, it'll tell us what that angle is supposed to be. Okay, so we want the inverse tangent of that ratio, which was 15/12. And that's going to be about a 51.3 degree angle. So x is approximately 51.3 degrees. Okay, it's a little weird, but the opposite of tangent is inverse tangent, and that will work similarly for the rest of these. So next example, this is our angle, this leg is adjacent, and this is the hypotenuse, so A and H correspond with cosine. So I'm going to say that the cosine of my angle has to equal A over H, the adjacent side over the hypotenuse. So in this one, I have to undo a cosine. That means x is going to be equal to the inverse cosine of this ratio. So the cosine of some angle being 7/12 that's another way to write that. Now we can approximate this with the calculator. Let's ask it the cosine of what angle gives us a ratio of 7/12, and it's going to say that's about a 54.3 degree angle. So 54.3 degrees. Okay, and then lastly here, we have this angle, and this is the opposite leg to that angle, and this is the hypotenuse, and O and H go with sine. So we're going to say the sine of some angle equals O over H, and hopefully we get an answer that makes sense on this one. So to get rid of sine, we're going to say inverse sine. So x is going to equal the inverse sine inverse of 8/16, which I know reduces, but let's just put it in the calculator. So we're going to go inverse sine. The sine of what angle gives us a ratio of 8/16, which was a half, right? It gives us 30 degrees. So it says x is exactly 30 degrees. Now, does that make sense for this particular problem? I hope. Okay, I hope that if we saw that this leg was 8, this hypotenuse was 16, this other leg would be an 8 radical 3, making this the smallest side of my right triangle, right, and across from the smallest angle, and then the 60-degree angle here, and across from that being the 8 radical 3, and the hypotenuse being double that smallest leg. So if you recognize that you had a 30, 60, 90, you can avoid using the sign to solve for that particular case. But this is another way for me to just kind of verify for you that you don't have to commit those special right triangles to memory, that you can still use sine, cosine, and tangent. Okay? Now, I don't know, how much of solving we're going to be working on throughout the unit, but these little details will be sprinkled in here and there, and it's good for you to be exposed to some of this before we get into some of the actual trig. Okay, so hopefully you've got enough to get going on your practice. As always, if you need some extra help, then just reach out. Until next time, take care.